Now in chapter 23, we take the same idea of proportions, and now we look at what about if we're dealing with two samples instead of one, or instead we're looking at a comparison between two different populations. So I sort of look at this as, in chapter 20, we talked about t-distributions and calculating confidence intervals and so forth for a t-distribution. And then we looked at, well, what if we have two different sets of data and we wanted to compare them? Then we could adjust our formulas to dealing with the difference between them instead. Sort of like, instead of, we had a one sample distribution for a confidence interval look like this: x bar plus or minus t star times s divided by our square root of n. And again, this was a t-distribution because we used the standard deviation of our sample to calculate the confidence interval. But then, as we went to two distributions, instead we looked at, well, what's the difference between the sample means? Because what we're trying to figure out is there a difference? And if there is, how confident are we in that? But otherwise, it's kind of the same idea. We take t star times the new standard error. And if you remember, the formula for that was s1 squared over n1 plus s2 squared over n2. And again, it's just sort of like, how do we adjust these things for dealing with two samples? Otherwise, the same structures. And the same thing will happen with proportions. So if we're looking at the formula for a confidence interval for the difference between two proportions, we would do p1 hat minus p2 hat, which is just like this. It's the difference in our two samples plus or minus. Again, we use z distributions for populations. Proportions. It's been a long day. Got up 16 hours ago and I'm hanging on by a thread via lots of caffeine. Anyways, and then it's multiplied by the standard error of the difference between those two, which if you look at this, notice it's pretty much the same idea. And we're replacing s1 squared, which is the variance, with p minus p1 for each of those two, which is exactly the same as we did before. Replacing this for a proportion, it's p times 1 minus p. So let's look at an example. Example 3 says, a researcher is studying adult men and women to determine their preferences for dating younger people. He asked them all who would be willing to date people at least 3 years younger than themselves. And a success is those, let's say, who answered yes. Basically, what percent of men would date someone who's 3 years younger than them, and what percent of women would as well. And let's just say, for the purpose of the survey, that 37 out of 50 men said that they would date much younger women, and only 14 out of 50 females would date younger men than women. And this data is completely made up, so don't make anything out of this. I'm not trying to be sexist with the data as usual. Just trying to make some data to look at the statistics. Anyway, so again, we can start by calculating. What we would say is this is N1 and N2, because remember, we have two different sample sizes as before. We would have the number of successes. And again, if we wanted to know, well, what's P1 and P2, it would just be the sample proportion for each, which is just the number of successes divided by the sample size. So for P1 hat would be 37 out of 50. Basically, that would be 74% of men who said yes. And with P2, it would be 14 out of 50. That is only 28% of women who said yes to this particular fictional survey. And we want to know, as usual, is there a significant difference between these two populations? Now, obviously, this is a pretty tremendous difference in percentage, but we need to factor in things like the standard deviation and what's the likelihood based on the data. And it will the actual percentages factor into this, but what's the most important thing is what's the sample size? How many people do we actually have? Because if we only survey 5 people, who's to know if this data is just based on random chance? So again, we could do a confidence interval on this data, and we could do a t-test. Let's start by calculating a 95% confidence interval to describe the difference in population. And remember, for 95% confidence interval, z-star is 1.96. This is one that we've used before, common number, but roughly within 2 standard deviations, 95% of the data falls in there, but that's a more accurate one. Again, you could look that up in table C or table A. You could figure it out as well. But that would be our confidence level of 95%. But that's we should have everything we need to know now to fill in our confidence interval. It might be nice to start with the standard error for the difference in the two sample proportions. So let's just do that first. The standard error here would be the square root of the sum of each of those divided by each of his sample size. So P1 was 74%. Again, you want to use decimals here. So 0.74 times 1 minus that would be 0.26. And that would be divided by the sample size 50. And then for women, their, which is P2 hat, their percent success rate is 28. And 1 minus that would be 0.72. And that's all divided by 50 as well. And so we could come up with our standard error here, which is, again, kind of like the standard deviation joined all together in one big clump. So we got the square root of 0.74 divided by 0.26 divided by 50. Whoops. This should be multiplied. Divided by 50. Then plus 0.28 times 0.72 divided by 50 as well. And that would give us approximately 0.0888 if we round to 3 significant figures. And now we should have everything we know to write a confidence interval. So let's write it and then we'll interpret. So we would have our confidence interval, just using the formula from above, should be the difference in those two. So P1 minus P2 would be 74% minus 28%. Again, I'll leave them as decimals as we should for formulas. And that would be plus or minus the z-score multiplied by the standard error. And this would, let's go ahead and calculate this out and try to figure out what this means. But we would have a 0.74 minus 0.28 plus 1.96 times 0.888. Sorry, there's a 0 in there. 0.888. And that would give us an upper value of our confidence interval of 0.634. And then the lower end of our confidence interval would be 0.286. And this is a pretty wide confidence interval based on the context, mainly because the data was so different to begin with. And we'd expect data that's this different is pretty certain to prove there is some sort of difference here. But basically what we'd conclude is, so these answers again are percentages. And remember that this is a measure of the difference between the two parameters. So if we were saying, well, what's the difference between P1 and P2? That would be the actual percentage of males who are willing to date younger people and the actual percentage of females who are willing to date younger people. We're concluding that we're 95% certain that it is somewhere between 28% and 63%. Now, that's not very certain, but we're pretty darn certain that men are more willing to date younger people than women. And this is basically how much more, somewhere between. So again, if we're trying to write out the conclusion here, we're 95% certain that men are between 28.6% and 63.4% more likely to date younger people. And remember, when you're dealing with a comparison, it's a little bit, you got to be careful with your comparison and what it actually means. But again, it's kind of like we have a difference between these two. If you just calculate the raw difference, 74 minus 28, I think this will make more sense. They're directly 46% more likely based on the data. And that kind of is the central value for our confidence interval, which is that right there. And we kind of expand it because we're not sure that's correct. That's just what we had in our sample. But based on the data size, we know that it spans somewhere around there, and that's what gives us our margin of error, which is this value right here, fairly large here, because we don't have a lot of data. Anyways, in the next video, we will do a Actually, sorry, not to wrap it up. Again, let's just check it with our calculator. Make sure we're doing okay and practice using the calculator. But again, this would be a confidence interval for a 2 sample proportion. So this would be a 2 prop z interval right here. We want to use this one. And we want to type in everything here. So x1 would be our number of successes for the first population. N1 is the sample size. X2 is the number of successes in the second population. N2 is the second sample size. And our confidence level here. And otherwise, again, very easy to do. We would get our confidence interval and we can check ourselves quite easily. Looks like we did well. And just like over here, actually, we did this one with a calculator too. I thought we forgot to for a second, but you know, you can always feel free to check yourself with a calculator. It helps you feel more confident, no pun intended, in what math we're doing. But as usual, I'll want you to show your work and do the math by hand on any exam.